everyone, welcome to the Geo Shed. Today I'm going to take you to Scott Construction Quarry, which is a quarry south of Green Bay, Wisconsin a little bit. It's currently being sold. We stopped by there on July 1st, 2021 and were granted access because of the reclamation activities that were going on. This video is a product of that visit. There will be some field footage. Usually in these Geophiles episodes I don't have field footage, but I have it for you today. But before I can take you here, I need to talk a little bit about the time span we're dealing with. We are deep in the Midwest, not that far from Lake Michigan, near Green Bay, Wisconsin. So the bedrock, excluding the glacial stuff and the modern soil and all that, is mostly from the Paleozoic era. Specifically, the Silurian and Ordovician. Behind me are the basic time frames for both of those. MA means millions of years ago. So essentially the Silurian was 419 to 444 million years ago. The Ordovician was about 444 to 485 million years ago. Now these rocks are not my specialty, but they are rocks I study. I just study much older versions of these. But there's something unique here. You see this southern polar ice cap here. Between these two periods, between the Ordovician and the Silurian, there was a southern polar ice cap. This is pre-Pangea. You've probably heard of that supercontinent. That had not formed yet. But the continents did cluster in the southern hemisphere a little, and so there a polar ice cap formed. There probably wasn't one in the North Pole. We can tell that by the sediments that we see. And there definitely wasn't any ice where Wisconsin sat at that time. The formations I'm going to talk about actually extend from the Green Bay area down through around Lake Michigan, through Illinois. They come down to Kankakee in Illinois, and they come back up into Indiana. But there's one unique formation that's well exposed here that is intermittently exposed along the way. But this southern polar ice cap was not an ice age event like we're in today, and it probably didn't last very long. But this is the time span where we notice it, because in North America, between these two periods lies something called an unconformity. I've drawn the geologic symbol for an unconformity here in red. An unconformity is a section of missing time in the geologic record. Sometimes we can determine exactly what that is, sometimes we cannot, and it can be any span of time that's noticed. But you gotta look at the rocks to see if there is an unconformity. You can't just imply one because you want to. It's gotta physically be there. It's just the amount of time varies on the situation. But the one in between the Silurian and the Ordovician throughout North America is probably about 444 to 445 million years old, around the middle of this ice cap. And what that did, well, you know what? I think I'm just going to take you into the field and show you the video, because I did record a lot there for you. You're going to see a strat column and stuff like that that I drew. So let's get started. The oolite, that's exactly what I'm looking for, is the oolite. Yeah, see that they got the red till above it. Yeah. Hello everyone, it's July 1st, 2021. Before I get started, as usual, any corrections or additions will be put on screen, so watch for those. But here we are in a quarry just south of Green Bay, Wisconsin. They were nice enough to let us in. I apologize for the wind in advance. There's nothing I can do about it. But there's a couple of things I want to show you here. This is obviously a bedrock quarry. They quarry the rock for construction purposes. Now, I wanted to go a little bit west of here, maybe a mile or so, because the contact between the Ordovician and the Silurian is exposed in a creek there, but it's on private land and it's protected. You can't get down there anymore. But I think we have it here. If you look at this rock right here, just laying around here, right where I'm standing, you see it's dark, it's pyritic, it's lot of pyrite in some of this. It's rusty when you grab it. Well, so technically it's a shale. It's fissile. It just breaks apart when you just dig into it, especially when it's wet. And you see some things like this here, which these structures right here are fossils. They're worm burrows. You might be like, well, that's cool. Why do they need shale for construction purposes? They don't. Most of the walls here are carbonate, limestones, dolostones. They're Silurian in age. And I'm pretty sure we're right at the contact between the Ordovician and the Silurian, like we were at Kankakee River State Park, 250 miles away. And the same formation that was the upper Ordovician at Kankakee River State Park is the same upper formation here, that Neda oolite. So we're 250 miles away. From what I can tell, the quarry floor seems to be the top of the Neda, at least right here. And you see these dark patches, it seems to be. We do know it's an uneven erosional unconformity, so it's probably not consistent everywhere. And you look at it, and it doesn't look like the Neda does at Kankakee River State Park. It's red and rusty, but it maintains a lot of that. It's green shale color, and it's got a lot of dark black and brown shales as well, which it does not have at Kankakee River State Park. And like I said, there's a bunch of pyrite here. We got some trace fossils, worm burrows, stuff like that. That's really makes this top of this formation a lot more interesting than it would be normally. We're standing on an ancient hill right here. This hill right here that we're standing on, well, it's not a hill anymore, but I'm standing on the top of what used to be a hill at the end of the Ordovician. And during the early Silurian, the ice caps in the southern hemisphere melted, the seas came back, we had more basin, continued basin subsidence, and we got these thick carbonates you see deposited around me here. They're not reef-like. These are inter-reef rocks. There's no reefs right here. So before I take you around and show you more spots here, or just point stuff out as we look around and explore, I want to show you this. This is the Neda, this is the Ordovician, and this is very typical of the basal Silurian carbonates. You can see there's white churton here. That's also very common in Illinois. We get very similar deposits, even though we're separated by hundreds of miles here. So I'm going to take you around the quarry a little bit, show you around. This is a good chunk of oolite. You can see a lot of it here, just all up and down right here. And you can see this is pretty typical, just like it is in Illinois. You can see the modeling with the gray shales. There's a lot of dark shales here, which aren't in Illinois. We have pyrite right here. A lot of iron staining, a lot of pyrite and a lot of this stuff. Look at it. Let's see if I can do this. See this right here? And you can't see because of the dust very well. Probably not on camera, but you see these two bumps right here? We have a little bit of stromatolitic development here. Not a lot, I don't see it in the rest of Silurian, just right there. I am not seeing a lot of fossils other than those little stromatolites. Not much here in the base of Silurian. Oh, probably here we have some bugs and vescules. So there's probably some fossils that weathered out of there. Right here, we are at the Ordovician-Silurian contact. That's what my right foot is upon right now. You can tell we have the Neda, that very fissile shale, iron-rich oolites, stuff like that below. And right here, where my foot is now, is the contact. This is a Silurian. What makes me think that? Well, this is very argillaceous. AKA means it has a lot of clay in it, but it is a carbonate. And although it's fissile like the underlying Neda, it has none of the characteristics. It does have a grayish green color, as the Neda occasionally does here, but it's prevalent here. It extends. It's this entire ledge, as you can see. And like I said, this is a carbonate. This is the base of the Silurian, because as those seas came back in after that southern ice cap melted, it would have had to have sourced some sediment from somewhere. And this area had a lot of argillaceous material, even though carbonates were trying to be deposited simultaneously. So the seawater would carry some argillaceous material and deposit it along with the carbonates. Now, carbonates and clastics usually do not deposit together in large quantities. You will occasionally get argillaceous carbonate or carbonaceous shales. That happens, but this is really argillaceous, and I just know. And if I didn't know it was a carbonate, I might even call it a mudstone. It's real close to that line, so this is an exception to the rule. But the key thing, the key reason why I know this is not Ordovician is the fact that we have chert in a lot of this. I just saw the piece of it here. See, here we have argillaceous carbonate, you know, close, very close border to a clastic mudstone. And you see you got this chert here. And then see right up here you have pure carbonate. So there's a transgression from this argillaceous material to this pure carbonate material. So there's no unconformity is what I'm trying to say. So this has to be Silurian. Quarry operator was nice enough to show us a couple of places. In this one here, you can see it's kind of mucky and gray. This is clay. I'm not sure if this is the top of the Ordovician or base of the Silurian. I want to say base of the Silurian. We are a few feet, maybe 3-4 feet, a meter higher in elevation than we were where I know the top of the Ordovician is for sure. And you do see some carbonates, strong carbonates here with a lot of pyrite in it, just like you do over there at the base of the Silurian, the argillaceous part. And this is very argillaceous, but it is carbonate. So I do think we're at the base of Silurian here. I don't think it is the top of the Ordovician, but it's close. It's probably less than a meter below my feet. As you can see, it was excavated from the pond over here, so it's probably even less than that, because you can see the purplish deep reds of the oolites pushed up in the hills over. So yeah, see here you can see the rock's better indurated here. We got 2 sets of fractures. So I believe this is basal Silurian, and this iron staining is just from it being exposed to the surface during quarry operation. But this has a lot of good pyrite in it.
Ooh, pyrite nuggets everywhere.
The Neda Formation exists throughout the Midwest and Wisconsin and Illinois. It apparently is absent in Indiana, although it's not that far from the border, as a bunch of isolated patches, if you will, or lenses on top of the Brainerd Shale, which is far more extensive and even goes into Iowa, extends into Ohio and becomes something known as the Cincinnati Group, which is far more complex. But the Brainerd and the Neda are part of what's called the Maquoketa Group in Illinois. In Iowa, it's referred to as a formation, or in Indiana as well is referred to as a formation. But the Neda oolite's unique because it was deposited in a shallow marine environment. We can tell that because modern oolites are also deposited in that manner. Basically, an oolite is just a little almost perfectly spherical ball of usually carbonate with something in the middle, like a mud grain or something, to form as a nucleus so that oolite can grow around it. But the Neda, although probably deposited as a carbonate, didn't stay that way. That ice cap in the South Pole that I told you about, well, that lowered sea level. And that was just enough to pull out these shallow seas that were upon the continents at the time. And at the time when the Neda was deposited, we're talking maybe in 50 foot of water. So the ice sheets in the southern hemisphere locked up enough water to pull those seas out and drop sea level about 200 feet. So about 150 feet lower than it previously was. And that allowed streams to become established because now you had exposed land. So the Neda, being the thinnest of these formations, and throughout most of Illinois and Wisconsin, it's less than 15 feet thick, but it can get up to greater than 30 feet thick. In some places in Wisconsin, the Neda can be thicker than 30 feet, where it's actually mined for iron. But wait, Steve, you said oolite-rich formations were calcareous, so how are they mining iron? Well, that sea regression exposed the Neda and the Brainerd mostly to the surface, allowing erosion and allowing the oxygen in the atmosphere to react with the rock. And we had something at this time called an oxygen crisis. Let's talk for another time, but basically it allowed for those upper parts to become rusted, if you will. A lot of calcareous parts were replaced with iron and iron carbonates. We see this throughout the geologic record. More recent deposits of the Clayton Formation in Georgia, which I visited, and they were originally carbonates, which have been almost totally replaced by iron minerals, and you can actually find iron fossils because fossils form through the replacement of organic parts by minerals. So the Neda got replaced with iron, and in some places it was a lot of iron, and you can actually still see some of the calcareous oolites. I didn't see them in the quarry, but I have seen them at Kankakee River State Park. So some of it's still unaltered. Anyway, that's it. If you have any questions or comments, please leave them below, and I hope you learned something. I have no idea whose exoskeleton this is. I mean, it's probably like a crawdad, but it just looks like a scorpion, doesn't it?